So moving on to concentrations and rates. So different equations or different chemical reactions have different rates that they occur. Now, they are not based on the coefficients in the reaction, because remember I mentioned something about mechanisms. So when I'm looking at a rate, we are going to be able to write what's called a rate law for each and every chemical reaction. It has its own rate law. Okay, so all chemical reactions have a general rate law, and what it does is it represents the rates dependence. So it depends on the rates dependence on reactant concentrations. Okay, so the rate usually depends on the concentration of the reactants, depending on how the mechanism occurs. Now, we did just say that the rates are stoichiometric. The rate law, however, is based on the mechanism, and you cannot actually look at the balanced equation to determine the rate law. So I made a note here, you cannot write it based on the balanced equation. The only way to figure out a rate law is if you are given data. Okay, you have to do an actual experiment and be given data to figure out a rate law. Or if I know what the mechanism is, which we don't usually. Okay, we'll talk about mechanisms again later. So this is what a rate law looks like. Okay, this is kind of an important thing to note up here. The rate law is written rate equals K. K is the rate constant. Okay, rate constant. Each equation or each reaction has its own rate constant. Okay, so this is specific to a reaction. All right. I do want to note the K will change with temperature. Changes with temperature. Okay, because different rates happen at different temperatures. So you do have to specifically say the temperature is not changing, but I won't change the temperature on you. So rate constant K times the concentration of the reactants raised to some power. Okay, it might be the power of 1, might be the power of 2. It might not be based on that concentration, depends on what the data says. And those are called orders. So the power is the same as the order. So if I say something is first order, that means its power is 1. Okay, that's it. All right, so like I said, the ways to determine the rate law are experimentally. Okay, so the only way to do that is to actually measure the rates of appearance or disappearance over time with different concentrations of reactants. Measure rates with different concentrations. So if you can see that the rate changes when you use different concentrations of reactants, you can tell if it depends on a certain concentration or not. Now you can also do it if you know the mechanism, and then you can kind of imply the law from those steps. And again, we're going to talk about that in the next lecture, okay? So you can figure out the rate law either of those two ways, but not by looking at the balanced chemical equation. So if I said write the generic rate law for this equation, remember you cannot use those coefficients. I don't actually know what they are unless I give you data. So the generic rate law, remember, is rate equals K, whatever the constant is, times the concentration of one reactant raised to some power, I'm going to call it M, times the concentration of the other reactant raised to some power N. And what we're going to do is we're actually going to figure out what those powers are based on data. Okay, so I'm going to help you guys out with example number 3 here. For the following reaction and rate law expression. So I gave you the reaction and I gave you the rate law. Again, notice the coefficients over here are 2 and 2, but this one is only second order with regard to nitric oxide and first order with regard to hydrogen. Okay, so again, we cannot carry those numbers over to figure out the orders. Okay, but I did give you the rate law, so I know for sure. It says, what are the orders of each component and the overall order? So if I asked for what are the orders of each component, what you're going to say is this reaction is second order with respect to nitric oxide, and it is first order with respect to hydrogen. Okay, and then it says the overall order. So the overall order is actually how many exponents there are. That's it. So 2 plus 1 is 3. So it is third order overall. Okay, that's it. It is as simple as that. Add up the exponents, right? The last thing says, what are the units on the rate constant K if the rates are in molarity per second? Remember I said rates are almost always going to be in molarity per second. So if you were ever asked to find the units, hopefully you can do a unit analysis, but all you have to do is plug in the units and find what they're going to be. So if I want to find the units for K, it says rates are molarity per second. So if this is my equation, I'm going to use this equation. I'm going to plug in to find the units on K. So rate is molarity per second equals, I'm trying to find the units of K, so that's my unknown, times NO, or brackets mean molarity, so that would be molarity of that squared. H2's concentration would also be in molarity, and that's to the first power. So if I solved for K, it would be molarity over seconds times molarity squared times molarity, which is really molarity cubed. And let's see, one of those molarities would cancel out. So the unit is actually 1 over seconds times molarity squared. These are the units on K. And that's actually going to be true for any third order reaction. So once you know what the K units are, you can just pull them in. You don't have to solve for them each time. Okay. All right. So example number 4 says for this reaction, A plus B makes C. It is determined that the rate law is this. What factor would the rate of the reaction increase if the concentration of A is doubled and the concentration of B is tripled? So this is a little bit different of a question, but all I want you to do is double A, so like put a 2 in there, and triple B, so put a 3 in there. You should be able to tell by how much the rate is going to change. So all I would do for this reaction is I'm going to rewrite my rate law down here. Rate equals K times A times B squared. And I'm going to substitute in these numbers. So what would happen? What would the rate of the reaction increase by what factor if the concentration of A is doubled? So I'm going to do rate equals K times now 2A, and B is tripled. 3B, remember that's squared. Okay, so that's really going to be rate equals K times 2A times 3 squared is 9 times B squared. So that equals 18 K A B squared. So it's going to be by a factor of 18. We can actually figure out how much it's going to speed up. Okay, now determining the rate law. I told you in order to determine the rate law, you either have to have data or you have to have a mechanism. So a lot of the times I'm going to give you data. All right, so I'm going to show you how to determine the rate law if it's first or second or third order or whatever it is. So their strategy is essentially to isolate a variable. So look at one reactant at a time and determine the rate of change. How the rate changed based on how the concentration changed. So if I doubled the concentration and the rate doubled, that would mean it was first order. If I doubled the concentration and the rate quadrupled, that would mean it was second order. And I'm going to show you how I do this. Okay, so I have this reaction and I have this data, how I'm going to compare the different trials. So first, I want to figure out what the order is for NO2. Okay, so when I say isolate a variable, I want to do 2 reactions where NO2's concentration changes, but I only want to change one variable at a time. So I'm actually going to use trials 1 and 2 because in trials 1 and 2, the CO concentration stayed the same. Okay, so I only want to change NO. So I'm using trials 1 and 2 because CO is constant. And you don't have to write that every time, but it's good for your notes. So I'm going to compare the rates. Okay, so from here to here. And I'm going to compare what I did to the concentration. You might be able to tell by looking at this. I obviously doubled the concentration. And then what happened to the rate? Well, it looks like it quadrupled, but I'm going to show you just to make sure. So I'm going to compare my concentrations. Okay, so that's obviously 2. I doubled the concentrations. And then I'm going to compare my rates. So that rate to that rate is about 4. Put about 4. Okay, it should always be a whole number. If you don't get a whole number, then you probably did something weird. So I want to know, essentially, I'm going to do 2. I double the concentration to what power equals 4. Okay, and you should be able to tell by looking at that, oh, well, X must be 2. That means NO2 is second order. Okay, now I'm going to do it again. All right, for CO, but this one, essentially I doubled that and this quadrupled. So that must be in its second order. Okay, I'm also going to do CO, and I want to put 2 experiments then when NO2 is the same. So I'm going to pick trials 2 and 3 because NO2 is constant this time. Okay, and I'm going to look at what I did. So I doubled the concentration again. So just to show you all the math, that is 2. I doubled the concentration. And then what happened to the rate? Well, if you're comparing those look about the same to me. But I doubled the rate, I doubled the concentration, and then I'm going to divide these. Now remember, this is an experiment, so it's not going to be perfect. That's about 1. So as I doubled the rate, as I doubled the concentration, the rate didn't change. Okay, so that must mean that the rate isn't based on the concentration of carbon dioxide. So I would do 2 to the x equals 1, and that means that x equals 0. So that means that CO is 0 order. Okay, so how I would write the rate law then is I would write rate equals K times the concentration of NO2. I said it's second order, so that's going to be to the power of 2. And then if it's 0 order, you don't even have to write it because anything to the 0 order is 1. So this is actually my rate law for this reaction. Okay, now I can calculate K and the units for K. So calculating K, you just kind of choose a trial. You can do any of the trials. I'm going to do trial 1 just for convenience and then plug into this equation. So the rate for trial 1 is 0.0021 molarity per second equals K is what I'm trying to find times I have NO2's concentration is 0.10 molarity squared. And then I solve for K. So I'm going to get the K is 0.21. And then if I do my unit analysis, this is going to be 1 over molarity seconds. Oh, oops. Sorry. Do that on here sometimes. I'm just boxing my answer. Give me that pen back. There. Okay. So that's my answer. K is 0.21. 1 over molarity seconds is the unit. All right. So essentially, based on that reaction, what you're going to see in the data for these orders, because usually it's going to be 0 first or second. Sometimes you'll see a half, but not very often. It's 0 order if I double the concentration and the rate doesn't change, stays the same. Same thing would happen no matter what I do. If I triple the concentration and the rate stays the same, that means that it was 0 order with regard to that specific reactant. Okay. Now, if it was first order and I double the concentration, then the rate would double. If I tripled the concentration, then the rate would triple. Pretty straightforward. Second order, if I doubled the concentration, that means it's raised to the power of 2, so then the rate would actually quadruple. So if I triple the concentration, then the rate would multiply by 9. It would be 9 times faster, okay, because it's got a power of 2. Now, again, I won't give you one that's a half order, especially when we're practicing and on the test and stuff. But if you see a half, it does sometimes happen. Essentially, what would happen is if I double the concentration, then the rate would actually decrease a little bit. The rate would multiply by √2. Or if I tripled the concentration and then the rate would actually decrease, or it wouldn't decrease. It would only increase by like 1 point something or whatever the square root of 2 is. Okay, so just kind of keep that in mind. All right. I am going to do example number 5 with you, and then I would try example number 6 on your own. Okay, so example number 5, given the following 3 experiments below, answer the following questions. I gave you the reaction. So these are my 2 reactants. So I need to find the order for each reactant. So I'm going to look at ClO2 first. I'm going to choose trials 2 and 3 because that's where OH minus is constant. And it looks like I tripled my concentration. Okay, so that's 3, right? I tripled the concentration. And I can see what happens to the rate. If you want to do the math, you can. 0.0248 over 0.00276 is about 9. Okay, So I'm going to actually do it up here. 3 to what power is 9? Well, X is 2. So this one is second order. All right, same thing for OH minus. I'm going to do trials 1 and 3 because that's when ClO2 is constant. Looks like I tripled again. This is a 3. And then I compare my rates are 0.00828 over 0.00276. Well, that's about 3. So 3 to what power is 3? Well, 1. So X is 1. So this is first order. So if I said write the rate law expression, you would go rate equals K times my first reactant to the second power times my second reactant to the first power. You don't have to write the 1 if it's understood. What is the value of the rate constant K? So I'm going to just choose trial 1 and plug things in. So the rate is 0.00828 molarity per second equals K times ClO2 squared. So 0.020 squared, oh, that's molarity, times 0.090 molarity, not squared. I would get that K is 230. And my unit is 1 over molarity squared times seconds. So this would be my answer. And it's third order overall. Okay, right? Because 2 plus 1 is 3. So I want you to try number 6 and then check your answer on here. I'll pop that up here in just a moment. Okay, so I've got all my work here. Essentially what I determined is that it's first order in hydrogen peroxide, it's first order in iodide, it's 0 order in the H+. So my rate is this. I plugged in my info, I got K, and then the part C asked for the initial rate, so I plugged in the information. Notice I didn't use H+ because it was 0 order, so it doesn't go in. And I got that my rate is 1.8 times 10 to the -5th. Okay,